All right, so it's 12.1, analysis of variance. We've tested claims about means from one or two populations or treatments. The methods discussed thus far do not allow comparisons of three or more means. In this lesson, we study analysis of variance, a tool which allows the comparisons of means from three or more samples. Analysis of variance is often abbreviated with the acronym ANOVA. In this lesson, we use ANOVA to compare means from three or more independent samples with a treatment applied to each. So a treatment is like a medical treatment. Okay, so that would be for an experiment. Or it could be a non-medical treatment with any kind of an experiment at a single level of dosage. You can also do what they call two-way analysis of variance, where you have multiple treatments at multiple levels, but we're not doing that. Okay. And by levels, I just mean like a dosage amount. Okay. So that's a really complicated two-way analysis of variance. With only one level or dosage applied to each sample, we're conducting one-way analysis of variance. Okay? One-way analysis of variance is greatly simplified if each sample has the same size. So that's what we're going to do. Sample sizes will all be the same. The examples in this lesson will use samples of the same size. If the sample sizes are different, we recommend using a computer and you won't have to deal with that. The term analysis of variance sounds intimidating, but don't worry. Variance, as you may remember, is just the square of standard deviation, and the test statistic that we'll use uses two different variances, and each of the variances has its own degree of freedom. Okay. So here we go. Are there differences between pain relievers? That's our example here. The following are temperatures of sick patients after taking different treatments for reducing fevers. Researchers want to determine if there are differences between the mean temperatures for patients who use these 5 treatments. We'll now test the claim using 1% significant. Because of the requirements for the test, we assume the samples are drawn from normal populations, which is a little tough, with equal variances, also a little tough. This is called a robust test. When we refer to a test as robust, it means that the requirements aren't really that strict. So the normality requirement, approximately normal is fine. Equal variances, that's probably not true. Tends to work out pretty well, even if it's not true. So it's not a real strict. Okay, I'm just going to walk you through the test. Again, you got body temperatures for people on 6 different painkillers. Okay, and mostly they're trying to reduce their body temperatures. So let's just walk through the steps here. Step 1, determine the hypotheses. Okay, so the hypotheses for the test are HO, the means for these populations are all equal. There's 5 of them, so you could say like mu1 equals mu2 equals however many means there are. We're going to say there are k samples, so you'll say up to mu k. Okay, and k is the number of samples. Okay, so you're testing them all at once. And then the alternative hypothesis just says that they're not all equal, basically. Okay, any questions? I'm going to bring my chat up here so you can see questions. Okay, then it's asking what are the null and alternative hypotheses. All right, fine enough. There are 5 samples, so k equals 5 here. Okay, so the null and alternative hypotheses with 5 samples, you can just say for the null hypothesis, the mean body temperature under all 5 treatments is the same. Okay. Alternative, well, we wouldn't know which one's different, so we just say the means are not all the same. Any questions about that? Super straightforward. Okay, let's go on. So on step 2, it says collect the data. One-way analysis of variance is a test which compares means from k different populations or treatments, and of course you have k samples as well. When comparing populations, samples should be random and independent. When comparing experimental treatments, members should be assigned to groups, they should be randomly assigned to groups so that the groups are similar. In this example, we are comparing means from 5 different experimental treatments. So K is 5 here. Analysis of variance requires that all populations are normal with equal standard deviations or variances. While these requirements are rarely satisfied perfectly, the test is robust. It tends to work well even when the requirements are not met. Okay? But obviously, the farther away you get from meeting the requirements, the less reliable the test, but it's a pretty tolerant test. All right, when conducting one-way ANOVA with equal sample sizes, we will need a sample mean and variance from each of the k samples of size n. Oh boy, okay, so we've got 5 samples and we need 5 sample means and we need 5 sample variances, which are the squares of the standard deviations. So if you don't mind, let's just do the placebo together, and then I'll give you the rest of these numbers, okay? So let's go back here. We're just gonna key in, get your calculator and wipe the memory and key in these temperatures for the placebo into your data editor. All right, does anybody have the mean? Yeah, that's what I got, 298.3, thank you. Now, you can see the standard deviation is 1.1, I think, which is oddly precise. Go ahead and square that because we need this to be a variance. Remember, this is called analysis of variance. So everything is a variance in this. We always square the standard deviation. So great, 1.21, thank you. All right, and the sample size, wasn't it 7? So there's that. Okay, any questions? Your square, that's the trickiest part to remember here is you got to square your standard deviations in this lesson. But otherwise, it's, these are all statistics you've done before. All right, I'm going to slide back a skosh and get the rest of these. So give me one moment. This is from I'm stealing it from last semester. Probably stole it from the semester before last semester. Just keep stealing them. Okay, here are the rest of them. I'm just going to give you guys a sec to paste all those in or write them in. Oh, great. And it looks to me, I have different versions of this lesson. This this version, and this version of the lesson does not explain things as much. Okay, now there's an assumption in this test. The assumption is that the variances are equal. I'm going to go ahead and just give you guys a little background. The assumption is that variances are equal. But also the null hypothesis says the means are equal. And when I say variances, I mean the population variances are equal. And the null hypothesis is another assumption that says the means are equal. Okay, don't forget, there's another assumption that says the populations are normal. So what if you stack all of these assumptions together, which are not strict, but we assume them, we're saying the populations are all normal. They all have the same mean and the same variance, and therefore the same standard deviation. And what you're saying is they're all identical. Okay, these are 5 identical populations. So they're essentially the same population. Okay, that's really what this is saying. And if the populations are the same, then you can just treat them as one. And so there are things that we know, if they're all just one population, I'm going to come up with an estimate for the population variance. So sigma squared is going to be the common population variance. Okay. And if I want to estimate sigma squared, there's a couple of ways we do this. Okay, the first way is we look at the standard error for sample means, standard error for X bar is sigma X bar is sigma of the square root of n. So that's from chapter 7, which tells us that now that has the population standard deviation in it. Okay, and I'm trying to solve for the variance. So I'm going to first solve this for sigma. Okay, so that sigma would be the square root of m times sigma X bar. Okay, and so if I square both sides, I have the population variance. So sigma squared would be just n times the standard the variance of the sample means. So I'm squaring these. And I know what n is. That's the common sample size. It'll be 7. Variance of sample means that's all sample means. I can't do all sample means, but I could do 5 of them. I've got 5 sample means, so why not do the sample standard deviations and just say this is approximately n times the sample standard deviation of the 5 sample means that I have above. Okay. Maybe I'll make a note here that Sx bar, this is going to be the standard deviation of the X bar values up above. Okay. And so if I could take the standard deviation of the X bar values, square that, multiply by the sample size n, then I'd have an estimate of the population variance. Okay, so that's one way of estimating the population variance. Another way of estimating the population variance is to just average the sample variances. So here we could estimate, sigma squared by averaging the estimates the S-square values. Okay. So we would call this sigma squared is approximately the sum of the S-square values over the number of them. There are K of them. Remember, there are K samples. Okay, and this is called the pooled variance. So we call this SP squared. Pooled variance. Pooled is just another word for average. Okay, so this gives a little more detailed notes. All right, so we've got this standard deviation, this estimate in the numerator, and this other estimate of the same number in the denominator. Okay. Those are estimates of the same value, so the F statistic should be close to 1. If all of our assumptions are true, okay? If all of our assumptions are true, these are two estimates of the same value. These should be similar if the null hypothesis is true. All right, let's go ahead and do a little more reading here. Okay, so I wonder if how much I skipped here. I think we're good. All right, so you can see this statistic that we're going to be computing. That's called F statistic. All right, it's after Ronald Fisher, who is very much prominent in a lot of the theory you guys have learned this semester. Also not a great person. I think he was also one of these guys that was deeply invested in eugenics in the 20th century, mostly the early 20th century. But he was a really smart guy, and also would have been viewed as a pretty horrible person nowadays. Anyway, that's the F distribution named after him. Okay, so let's just review here. The symbol SX bar squared, this one up here, represents the variance, that is the squared standard deviation of all sample means. Symbol SP squared represents the pooled variance. This is just the mean of the variances. That's this one. Okay, and you just take these two estimates of the population variance, divide them, and you should get this F statistic. And this should be close to 1 when the null hypothesis is true. All right, so we need to do some of these computations. So if you'll step back and on your calculator, just key in the X bar values. So there are 5 X bar values. So here, what's the variance of the sample means? Here we want you to clear your memory and key in all of the X bar values to get their standard deviation. Okay, so let's do that real quick. So again, I just want the standard deviation as sample means. Anybody? Let's be real quick. That's the mean of sample means. Remember, we want the standard deviation. Okay, so this, okay, so Sx bar, this is the standard deviation of the X bars. Okay, 1 point. Now, it looks like you, that's not what I got. Yeah, let's get a second opinion on this. I'm gonna check my data. So yeah, how about that? We're getting off now. Hey, Andrea, is that squared already? Okay, now we're getting warm. Okay, so what I want to write is the 1.1104 that I also got, and then squared. Okay, and I'm going to double check everything. 1.1104. Now there's actually a lot more digits here that I'm going to keep. So I'm pressing, I'm typing the whole precision in. And when you get this, it comes out to exactly 1.233. And yeah, Andrea, that's perfect. Good, 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 good. So that's an S, that's, yeah, that's standard deviation of the sample means. Now we have to do the pooled variances, okay? Pooled variance is SP squared. That's just the average of the variances. This is the mean of the S square values, so don't square the result. It's just a mean of variances, okay? Don't do any squaring here. So add the variances up and divide by 5. You don't have to use your fancy stats for this. So right now you're adding 1.21 plus 1.05 and so on. Okay, thank you, Susan. That's the, and Andrea, that's exactly what I got too. 1.124. Okay, so that's an estimate of the population variance. Okay, so it says, is the sample size the same for each sample? Yeah, they're all 7. So this whole method requires that the samples all have the same size. So yes, N is 7. Good Lord. All kinds of noises going on here. Sorry, you guys. So N is 7 for each sample. Okay, going on. What's the common sample size? I just said it, 7. Okay, what's the value of the F statistic? Well, the numerator takes N, which is 7, multiplies by the Sx bar squared, which is a 1.233. Okay, I think that's already squared, so don't square it again. Biggest mistake people make is to square stuff that's already squared here. The next one is 1.124. Okay, now I want to go ahead and do one step here. Just multiply the 7 times the 1.233. Okay, you should get 8.631. Over the other one, which is obviously 1.124. Okay, now these are both estimates of sigma squared, the population variance. So I want to make the note here, these estimates of sigma squared are very different. What went wrong? Remember, F should be, those two numbers should be similar. So the F statistic should be close to 1. Okay, but that's under a bunch of assumptions we've made. Okay, so what's gone wrong is that the numerator is too big. The numerator has the standard deviation of the sample means. Okay, what did we assume about the sample means? Right here, we assumed that the means are all equal. Okay. Under that assumption, we came up with an estimate of the population standard deviation that involved taking the standard deviation of all the sample means, which should be similar if the population means are all equal. But the sample means aren't very similar here because their standard deviation is coming out much bigger, and that's why this numerator is coming out too big. There's too much variability in the sample means. So the standard deviation is getting too big, and my two estimates of the population variance is coming out way bigger than 1 because of the fact that it looks like the null hypothesis can't be true. Okay. Any questions about that? Okay, so let's finish this computation down here. So kind of about 7.679, I guess. Okay. That's 7.6 times, you know, this is much bigger than it should be. Should be close to 1 if the null hypothesis is true that the means are all equal. Okay, let's read this. It says the idea behind the test statistic is not too complicated. Well, you can be the judge of that. When the null hypothesis is false, the sample means should be very different, like ours apparently are, and their standard deviation will be large, like ours is. Remember, that's this number right here. Okay, it's coming out too big, and that's why this is coming out, the numerator is coming out so much bigger than the denominator. Okay. This will yield a large test statistic and a small p-value in the right tail of the distribution of F statistics. This is why the F test is always a right-tailed test. Okay, make sure you see that. Okay. To compute p-values, we obviously need to understand the distribution of such F statistics. Because the F statistic is a ratio of positive numbers, the F statistic is always positive. The distribution starts at 0 and is skewed to the right. The mode under the highest part of the graph is near 1. So the F statistics that are greater than 1 are usually in the right tail. So you can see the picture of how this works. It's just another one of these skew right distributions because it has to start at 0. The F statistic cannot be negative. Okay. Because there are two variances or standard deviations used in an F test, the two measures for degrees of freedom exist. For the variance in the numerator, the degrees of freedom are k minus 1. This is 1 less than the number of sample means. So you're just doing a standard deviation of the sample means. There are k of them, so there are k minus 1 degrees of freedom. For the variance in the numerator, the degrees of freedom are k minus 1. I just read that. The pool variance in the denominator, we averaged k sample variances, each with n minus 1 degrees of freedom. So the denominator altogether, you have k times n minus 1 degrees of freedom. And we use technology for the p-values for the f-test. So let's go ahead and do our backup here. K was the number of samples. I think that was 5. And N is the common sample size. If you go back and check, it was 7. Okay. So degrees of freedom for the numerator, again, you've got two variances here. Degrees of freedom for the numerator is just k minus 1. So that'll be 4. Degrees of freedom for the denominator is div 2. That's k times n minus 1. So that, again, k is 5. And then n is 7, so 5 and 7 minus 1. That's 6 times 5, which is 30. Okay. I don't know what our alpha is here. We're supposed to look up a critical value on table A5. So let's go back and look at our alpha. So it says, if you look at way back, it says this is a 1% significance on this one. Pretty strict requirement. It's a hard. So our alpha is 0.01. And we got these two different degrees of freedom. Now it's referring us to table A5. I hope it's at the end of this material. There, oh my gosh, it's sideways too. So it's a 4-page table. So you can look at the back for table A5. I'm going to bring one up here that's horizontal. I think if I've got it here. Well, this is a tragedy. I don't want to look at a sideways one. And I don't think the Notability lets me turn pages. I know Adobe does. Give me just 1 second, you guys. Um, all right, so I can do it this way. Just 1 sec. Okay, here we go. Sorry, I had to load this into Adobe and rotate the pages. So here it comes. I hope you're seeing the page. So let me bring up the first page of the table. Maybe you can see there's an alpha of 0.01 on the first page of the table. Okay, 0.01 alpha. The next page, still 0.01 alpha. Next page, 0.05 alpha. Next page, 0.05 alpha. So those are the only alphas you're allowed to use with these tables. Distributions are getting complicated, so they get limited. As the tables get limited as to what they can provide. But if you look, remember, for degrees of freedom 1, we had 4. So I see that here, okay? And it was 30 degrees of freedom for the denominator. So I'm going down. Now, if you can see my little hand here, but I'm hovering over 4 again for the numerator, and then going all the way down to 30 for the denominator. And it says 4.0179. Remember, this is always a right tail test, 4.0179. Okay, let's draw a little picture of that. So, table A5, DF1 was 4, DF2 was 30. Use the alpha equal 0.01 part of the table. And then we came in like this. And we got 4.01, is it 75? 79. 0179. Okay. That's just a critical value. That's not a p-value. Okay. So that tells you what significantly large is when the null hypothesis is true. So if the null hypothesis is true, you really shouldn't get a test statistic bigger than 4.0179. It would only happen 1% of the time that you would get a test statistic larger than that. And we have one that's larger. Keep in mind our test statistic is 7 point something, 7.679. So way, way up there is our test stat. So this indicates because it's so much higher than it should be, it indicates a rejection of the null hypothesis. The sample means are varying too much for the population means to be equal. You just have to reject the null hypothesis. Any questions? Okay, so we've got that. Now they want us to do the p-value. So this time on question 11, we want to put that test statistic. That's the 7 point, I gotta look it up again. 7.679. Is the test stat. Okay, and then our p-value will be this tail here. Okay, so next we have to go to our p-value calculator. So I'm going to go over to Canvas. And I'll share that in one moment. Okay, so just to remind you, let me do the share real quick. Okay, got the right one here. Okay, so on your home page in Canvas, you see on yeah. So there's a thing up on top that's now called important bits. That's where the final exam review is, and also a document that has all your formulas and tables. So if you want just one reference for formulas and tables, feel free to go in there. Yeah, and you can put, oh, I've got the flowchart too. Cool. More formulas, tables, 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 etc., etc. Okay, so that's formulas and tables, but also the p-value calculator. So finally, we're doing the F distribution, which is Fisher's F, the very last one. Okay, we'll just click on that. And then you dial in your 2 degrees of freedom. I think the first one, was it 6? Or was it 4? I don't know. It was 4. Okay, so dial that in, and the distribution shape depends on these. Degree of freedom 2, I think, was 30. Okay, and then you need to put in your F statistic. So ours was 7.679 there. And then down below, you'll see your p-value. Okay, it's always a right tail test. You can't make it out at all here, but presumably if I zoom in on that, I'll be able to see a shaded tail. I don't see anything except for, I think, getting closer and closer and closer. There it is. There you go. 7.679. You can see the shaded tail there, whose area is practically 0. So the p-value is 0.00. Let's just say 0.00022. Okay, so let me pop on over onto my iPad again. Okay, so we got our p-value in here. And we can say this in 2 different ways. Remember, the test statistic is, oh wait, I'm a little too ahead of myself here, so let me cover the p-value down. Yeah, so here's the p-value. And maybe just we give you a reminder here, we're using the p-value calculators. In Canvas. 10. And what does the p-value tell about the null hypothesis? Well, the p-value is 0.00022. This is less than 0.01, which is our alpha. Okay, which tells us to reject the null hypothesis. Alternative, we would support the alternative. Okay, the means are not all the same. So H1 said not all means are the same. And remember, you're trying to lower the patient's body temperatures with these pain meds. Okay, that's the point of the experiment. And so if the means are not all the same, you're saying that some of these treatments work better than others. Okay, so we'll look at those in a sec. But the data support the claim. That the mean body temperature differs depending on the treatment. And I just like to point out the standouts. So the highest mean and the lowest mean, just to kind of show the range and which ones are standing out. So let's look at the data again real quick. Where to go? Right here. So if you look, where's the highest body temperature? Yeah, and but for what treatment? Placebo is bringing the body temperatures down to worst. Okay, and which one's doing the best job at bringing down body temperature? Yeah, Tylenol. I don't know. Tylenol is supposed to be really bad for your liver or something like that. You can't take too much of it. It's nasty business. But Tylenol's good at reducing body temperature as long as you don't take it too long, right? I don't think any of these are supposed to take too long. They all seem to be somewhat effective, but the placebo is not. It's just not. It's totally different from the others, and the Tylenol seems to be the best one. These differences are statistically significant, meaning it's not just chance. You follow me? We can see they're different, but we don't expect them to be the same. Okay? The testing procedure is to say, well, are these differences because of some fundamental difference in the treatments? Is it chance or is it a true fundamental difference? And we've decided it's not chance here. So that's the importance of this procedure. We're able to scientifically and objectively look at differences and talk about when they are meaningful or when they're just sort of chance and random. Okay, I couldn't see that by just looking at this. There's no way to know by just looking at it. So these probability tests basically saying there's I mean, if you look at the p-value, the probability is basically 0 that these differences are due to chance. That's what the p-value is measuring. It's not chance. These treatments work, right? Some of them really well, some of them not so well, but that's good to know. Right, so let's write this in. Highest mean was for the placebo. That's what you want. The lowest mean was for the Tylenol. All right, guys, that's it. It's 9:30. We're going to do the review next, but I want to go ahead and start with our break. So I'll see you at 9:40, and then we're going to drive into this.